Premature motor bearing failure in variable frequency drive, or VFD, systems can be a significant issue, leading to downtime and increased maintenance costs. The description of 8 amps flowing through the equipment grounding conductor, or EC, and the observation of fluted bearings strongly suggests electrical current is passing through the bearings. This phenomenon is often related to the VFD and its associated wiring. Several factors could be contributing to this problem. Firstly, induction can occur where electromagnetic fields generated by the VFD cables induce current in the EGC and surrounding conductors, including the bearings. This is exacerbated by the proximity of the cables, especially when feeders on both the line and load side of the VFD share a cable tray system. The lack of magnetic shielding around the motor also increases the susceptibility to induced currents. Secondly, ground loops, where improper grounding connections or multiple ground paths can create circulating currents that flow through the motor bearings. This can happen if there are unintended paths for current to flow back to the source, other than the designated grounding conductor. Thirdly, capacitive coupling, where capacitance between the VFD cables and the motor case can allow current to flow through the motor frame and bearings. This is more prevalent with longer cable runs and higher switching frequencies of the VFD. To diagnose and address this issue, consider the following troubleshooting steps. 1. Isolate the cable tray. Verify that the VFD cables are properly segregated from other electrical cables in the tray. Consider using metal barriers or conduit to minimize electromagnetic interference. Segregation helps to reduce the inductive coupling between the VFD cables and other conductors, which in turn minimizes induced currents in the grounding system and bearings. 2. Check grounding connections. Ensure that all grounding connections are tight, secure, and properly sized. Verify that the ground grid is adequate for the system size and that it meets relevant standards such as those outlined in the National Electrical Code, or NEC. A properly designed and maintained grounding system is essential to provide a low impedance path for fault currents and to minimize voltage differences between different points in the system. 3. Eliminate ground loops. Use a grounding continuity tester to identify and eliminate any ground loops. This involves checking for unintended current paths and ensuring that all grounding connections are made at a single point to prevent circulating currents. 4. Reduce capacitive coupling. Install capacitors, also known as capacitive filters, between the VFD cables and the motor case to mitigate capacitive current flow. These capacitors provide a low impedance path for high-frequency currents, diverting them away from the motor bearings. 5. Install isolation transformers. Consider installing isolation transformers between the motors and VFD to provide electrical isolation and reduce induction. Isolation transformers break the direct electrical connection between the VFD and the motor, preventing the flow of common mode currents. 6. Use shielded bearings. Utilize motors with shielded bearings to minimize the effects of electromagnetic interference. Shielded bearings provide a barrier that reduces the amount of current that can flow through the bearing surfaces. Additional considerations include inspecting the motor cables for any nicks or damage that could compromise the insulation. Damaged insulation can increase capacitive coupling and lead to ground faults. Also, check the VFD settings to ensure they are optimized for the motors and application. Incorrect settings can lead to higher switching frequencies and increased harmonic distortion, which can exacerbate the problem. Consult with the VFD manufacturer for specific recommendations on minimizing current flow through bearings, as different VFD models may have different mitigation strategies. Finally, monitor the motors regularly to track the condition of the bearings and identify early signs of degradation. Regular vibration analysis and bearing temperature monitoring can help detect problems before they lead to catastrophic failures. Understanding the different types of grounding is very important. Grounding comes in several forms, each serving different purposes within an electrical system. There is equipment grounding, system grounding, and surge protection grounding. Equipment grounding is essential for safety, providing a low impedance path for fault currents to return to the source, thereby tripping over current-protected devices like circuit breakers or fuses. System grounding involves connecting one of the current-carrying conductors, typically the neutral, to ground at the source, such as a transformer or generator. Surge protection grounding is dedicated to providing a path for transient voltages, like lightning strikes or switching surges, to safely dissipate into the earth. The NEC provides detailed guidelines for grounding and bonding to ensure electrical systems are safe and reliable. Article 250 covers the general requirements for grounding and bonding, including conductor sizing, connection methods, and specific rules for different types of systems. Section 250.4 outlines the general requirements for grounding and bonding of electrical systems. It emphasizes the need to create a lower impedance path for fault currents to facilitate the operation of overcurrent devices. Section 250.24 details the grounding requirements for separately derived systems, such as transformers and generators. It specifies how the grounding electrode, conductor, and bonding jumper should be sized and connected to ensure a solid ground reference. Section 250.118 lists the acceptable types of equipment grounding conductors, including wire, cable, and metal raceways. It outlines the requirements for ensuring these conductors are mechanically strong and electrically continuous. Section 250.122 provides guidelines for sizing equipment grounding conductors based on the rating of the overcurrent protective device. It includes tables and formulas for determining the appropriate conductor size to handle fault current. Section 250.166 covers the grounding requirements for systems over 1 kV. It specifies additional requirements for grounding electrode systems and bonding to ensure the safe dissipation of fault currents at higher voltages. Understanding the different grounding electrode systems is also important. Grounding electrode systems are critical components of electrical safety, providing a connection to the earth for the purpose of stabilizing voltage, limiting overvoltages, and facilitating the operation of overcurrent protected devices. There are several types of grounding electrodes, each with its own advantages and suitability for different applications. One type of grounding electrode system is a metal underground water pipe. This is a commonly used grounding electrode, especially in older installations. The metal water pipe must be in direct contact with the earth for at least 10 feet to qualify as an effective grounding electrode. It provides a large surface area for dissipating fault currents and is generally reliable. However, the increasing use of non-conductive pipe materials can limit its effectiveness in modern systems. Another type of grounding electrode system is a ground ring. A ground ring consists of a bare copper conductor, typically number 2 American wire gauge, or AUG, or larger, that encircles a building or structure and is buried directly in the earth at a depth of at least 2.5 feet. This type of grounding electrode provides a comprehensive grounding system with a large surface area in contact with the earth. Another type of grounding electrode system is ground rods and pipes. Ground rods are metal rods, typically made of copper or copper-clad steel, that are driven into the earth to provide a grounding connection. They are commonly used in residential and commercial applications. Ground pipes are similar to ground rods but have a hollow construction. The NEC requires that ground rods and pipes be at least 8 feet long and driven into the earth to a depth of at least 8 feet. If multiple ground rods are used, they must be spaced at least 6 feet apart to avoid overlapping spheres of influence. Another type of grounding electrode system is concrete encased electrodes. A concrete encased electrode, also known as a UFA ground, is a grounding electrode encased in concrete. It typically consists of a length of bare copper conductor, number 4 AWG or larger, that is encased in at least 2 inches of concrete near the bottom of a foundation or footing. Concrete encased electrodes provide a very effective grounding connection due to the large surface area in contact with the earth through the concrete. Another type of grounding electrode system is plate electrodes. A plate electrode consists of a metal plate typically made of iron or steel that is buried in the earth to provide a grounding connection. The plate must have a surface area of at least 2 square feet and be buried at a depth of at least 2.5 feet. Plate electrodes are less commonly used than other types of grounding electrodes due to their limited surface area and difficulty of installation. Another type of grounding electrode system is other local metal underground systems or structures. This category includes any other metal underground systems or structures, such as metal tanks or building frames, that are in direct contact with the earth and can provide a grounding connection. These systems or structures must be effectively bonded to the electrical system to ensure a low impedance path for fault current. In addition to the types of grounding electrodes, the NEC also specifies requirements for the grounding electrode conductor, which is the conductor that connects the grounding electrode to the electrical system. The grounding electrode conductor must be sized according to NEC Table 250.66, based on the size of the service entrance conductors. It must also be securely connected to the grounding electrode using approved methods and connectors. Proper installation or maintenance of grounding electrode systems are essential for electrical safety. Grounding electrodes should be inspected periodically to ensure they are in good condition and free from corrosion or damage. The connections to the grounding electrodes should also be checked to ensure they are tight and secure. In areas with corrosive soils, it may be necessary to use corrosion-resistant grounding electrodes or to provide additional protection to prevent corrosion. Understanding and implementing effective grounding practices is crucial for minimizing the risk of electrical shock, fire, and equipment damage. The NEC provides detailed guidelines for grounding and bonding to ensure electrical systems are safe and reliable. It is important for electrical professionals to be familiar with these requirements and to follow them carefully when designing, installing, and maintaining electrical systems. When dealing with VFD systems, it is essential to consider the specific grounding requirements and recommendations provided by the VFD manufacturer. VFD can generate high-frequency noise and harmonics that can interfere with the operation of sensitive electronic equipment. Proper grounding and shielding techniques can help to minimize these effects and ensure the reliable operation of the VFD system. Moreover, the VFD system should have proper grounding as described by the manufacturer. This would include grounding the motor and VFD to a common ground point. The system ground is typically at the source. When working with electrical systems, it is important to follow all applicable safety procedures and to use appropriate personal protective equipment, or PPE. Only qualified electrical workers should perform electrical work, and they should be thoroughly familiar with the hazards involved. Electrical hazards include shock, arc flash, and arc blast. Shock can occur when a person comes into contact with an energized conductor or component. Arc flash is a dangerous condition that can occur when a short circuit or fault occurs in electrical equipment. Arc blast is a pressure wave caused by an arc flash that can cause serious injury or death. To protect against these hazards, electrical workers should wear appropriate PPE such as insulated gloves, safety glasses, and arc-rated clothing. They should also use insulated tools and equipment and follow lockout/tagout procedures to de-energize equipment before working on it. Lockout/tagout is a safety procedure that is used to prevent accidental energization of equipment during maintenance or repair. It involves disconnecting the equipment from its power source and placing a lock and tag on the disconnect switch to prevent it from being turned on. This is important to ensure that the equipment will remain de-energized and in a safe state. Working with VFD systems requires a thorough understanding of electrical safety principles and practices. By following these guidelines, electrical workers can minimize the risk of injury and ensure the safe operation of electrical systems. In summary, addressing motor bearing failure in VFD systems requires a systematic approach that considers multiple factors, including induction, ground loops, and capacitive coupling. By implementing the troubleshooting steps outlined above and following best practices for grounding and bonding, it is possible to mitigate the risk of bearing failure and improve the reliability of VFD systems.